All right, so good afternoon, everyone. My name is Neil, and today I'll be presenting my work FIXX, Finding Exploits from Examples, which has been accepted in the proceedings of the 34th USENIX Security Symposium held in Seattle last month. And this work was co-authored with Yashashvi, Professor Rigel, and Professor Venkatakrishnan. Okay, so 2024 was a year of exploits, specifically zero-day exploits. And what we found is that most of these revolve around the vulnerability known as taint-style vulnerabilities, which are when malicious data flow from input locations known as sources to locations that carry out the sensitive operations known as sinks in the web applications. And given that there are so many vulnerabilities, and even today there are so many vulnerabilities out there, there are many approaches and methods which are used to detect these kind of vulnerabilities. The most common of them being SAST or static application security testing tools, which use methods like symbolic execution, constraint solving to detect the vulnerabilities, which are then disclosed to developers and also reported as CVEs. However, what we found is that most of the CVEs that have been reported often focus on just a single instance of this vulnerability that has been detected. And because of this, there are numerous limitations that these tools have, such that they report the CVEs that don't have enough information or do not detect all possible cases of the vulnerabilities. And also due to these, because of this, numerous vulnerabilities go undetected. And since these tools are able to find just one vulnerability at a time, they contain they have multiple false negatives present in them, which is limiting them from discovering all possible cases of the vulnerabilities that exist. Which we can understand better. Let's look at an example. Here we have a CVE which was inspired by the application Code Astro Management, and this CVE contains a disclosed exploitable path as shown in the code of the application here, where we can see that two sources are present, which can be infiltrated with the malicious inputs, which are then sent to the database as shown by the query here, and then retrieved and executed elsewhere in the application as shown by the sink present over here. However, even though this CVE has been, the path has been discovered and the CVE has been reported, there does exist another similar undisclosed vulnerability elsewhere in the application as shown by the code on the right, where we see that there are two source statements, which again can be infiltrated with malicious inputs and then sent to the database via the query shown over here, and then retrieved and again, executed in these two sink locations elsewhere in the application. However, this vulnerability shown on the right hasn't been reported as a CVE, and the exploitable path hasn't been discovered, and reported as a CVE as well, or sent to the developers for patching. So this is where we present our main problem, where we say that whether any approach that's been is used to detect vulnerabilities, whether they're able to detect all possible vulnerabilities or every possible instance of exploitable paths, which is also what the team at Google, Project Zero, focused on, where they say that 1 out of every 4 detected zero-day exploits could have been avoided if a more thorough investigation and patching effort were explored. They also say that a correct patch is one that fixes a bug with complete accuracy, where they say that no other vulnerability or a variant of that vulnerability can further be discovered. And we frame our main problem statement based off this, where we say that given a disclosed vulnerabilities, are there other similar undisclosed vulnerabilities which haven't been found or detected and haven't been reported as CVEs? Shown in the statistics here, we see that there were a bunch of CVEs that were published in the year 2024 and 2023, 25% of them being not needed and required because they were just variants of the main vulnerabilities that were reported in these CVEs. So if a thorough investigation and patching was to be done, these extra unnecessary CVEs could have been avoided, and they didn't have to be published because they could have been included in the original CVE itself. Which jumps into our main solution, where we present FIXX, our approach FIXX, where we say that using the information present in the CVE, are we able to detect all possible instances of the vulnerability path that's present in that single CVE itself? So rather than focusing on finding new zero-day exploits, we aim to find our goal would be to reduce false positives in the detection of the paths by the current approaches and discover every possible instance of an exploitable path. So we do that by taking the information present in the CVE itself, executing that vulnerable path that's shown or exploitable path. And then using that, our approach finds similar paths elsewhere in the application, leading to many more, similar exploits, which are then reported as new CVs, and this time they're more, comprehensive. So let's look at the steps by how FIXX performs this. The step one being what we call the exploit executioner. So the first step would be obtaining details from the CV and then reproducing the exploit using a malicious payload. Once that is done, we obtain a trace of the code for which the exploit execution occurred and obtain the paths from the source to the sink. This exploit data flow path is extracted from the trace, and we term that as the exploit path, which is the path that is present from the source of the sink according to the steps shown in the CV and how it can be reproduced. And we add control dependencies to create a complete subgraph and obtain the thorough structure of this the graph in which the path itself is present. So before jumping into how we discover similar paths in comparison to the original path, which is what the main goal of FIXX is, let us look at the two similarity notions that we discuss in this paper. The first of which being the instruction similarity, where we say that two instructions are in the graph of the application are similar modulo x, where x is just a non-negative integer that we introduce. We say that they're similar if their AST subtrees have the same structure. So the abstract syntax tree needs to have the same structure and node types, and their X corresponding name nodes that are different, which is easier to understand by looking at this example over here, where we see that there are two instructions, as shown by the two lines of code present over here, and their AST subtrees have been shown to the left and right respectively. And we see that the structure as well as the types of these nodes are exactly the same, except for two name nodes, ret_conf and ret_value, which are different in these two lines of code. So we say that because there are two name nodes that are different, these two instructions are similarity modulo 2. And the other notion which we introduce here is the path similarity, where we say that a detected path is similar to the original exploit path if it has n% of instruction nodes that are also similar modulo x, and n is greater than or equal to the provided threshold. So if you have the original exploit path present in the left graph shown here, we say that the right graph is similar to the left graph if 80% was the threshold, and since it has 4 nodes that are similar to the left one, we say that it is 80% similar, and if the threshold was set, that would be that the right side path is similar to the left one. So using these similarity notions, let us jump into how FIXX aims to find similar exploitable paths using two novel metrics that we introduced in this paper, known as the reusability score and the sensitivity score. So the reusability score for an instruction would be just how often that instruction is repeated in the code itself, and the sensitivity score would be the cruciality or the importance of an instruction towards an exploit, to discover an exploit. And FIXX combines these two scores, but multiplying them to obtain the selectivity score, which is how these important instructions from the data flow path are selected. So looking at the example here, we see that, given that there's a graph or the data flow path specifically, we categorize based on the scores for each instruction themselves, the red nodes to be the important instructions because they're highly reused elsewhere in multiple locations throughout the application. So the single red node here is reused multiple times, as well as it plays a vital role in its sensitivity. It's pretty important in reaching the sink and executing the input that was sent. So it's also highly sensitive. So that being said, it has a very high selectivity score, and we term that, and FIXX deems it as an important instruction, which is what we call seeds in the paper. So FIXX extracts these seeds from the exploitable path, and then these are the ones that have high reusability and sensitivity scores. And these seeds are used to find similar instructions elsewhere in the application using our instruction similarity that we just discussed a while ago. So if we have a seed instruction shown here on the left, we see that there are other candidate instructions that can be present elsewhere in the application, which are similar to the seed instruction based on their structure, obviously, and the name nodes, which as per the modulo value that was set, if there were 2 name nodes that are different, we term that as similar modulo 2. If there are 3 name nodes that are different, for example, ID compared to RET, ID compared to value, and post compared to get, we term that as similar modulo 3. And we select the instructions according to the module value that was set. And using this, we were able to find multiple instructions that are similar to the original seed instruction, which leads us to the FIXX's final step of how it uses these candidate instructions to detect and verify the similar paths. So FIXX detects paths from source nodes to the candidate instructions that are similar to the original seeds, as well as D paths from the candidate instructions to sinks, and it uncovers these exploitable paths that are similar to the original exploitable path using these two subpaths known as S paths and D paths. FIXX then performs symbolic execution using the inputs from SMT solver, and eventually verifies if the similar path has been is executable. So using a figure to understand this, we see that given the candidate instructions which are similar to the seeds themselves, we proceed to find S paths, which are paths from source nodes to the candidate instructions, and then D paths, which are paths from the candidate instructions to the sink. And once we have the S paths and D paths, FIXX performs a symbolic execution using Z3 as its SMT solver, and then discovers exploitable paths and then verifies them. So we saw that we have a bunch of metrics. FIXX uses a few metrics as a threshold, a singular modulo. So let's see how FIXX has been evaluated for all this. So we select a ton of applications, which are specifically 19 applications, which revolves between with a few lines of code to about 255,000 lines of code, spanning about 10,000 PHP files. These are popular applications based on their GitHub star, as well as their frequency of how it's being used. And we select a total of 300 CV entries and reproduce about 132 of them, out of which we find additional similar paths for 32 CVs, spanning 19 applications, like I said. And the results that we have submitted give us 10 new CVs from Mitra. And we also compare FIXX with other vulnerability detection tools, which I will discuss in the next few slides to prove its efficiency. Okay, so looking at FIXX's performance, we see that FIXX first initially, like I mentioned, it selects the highly reused and sensitive instructions as seeds, and most of the applications that were selected had a really high selectivity score, which is a combination of reusability and sensitivity. And the FIXX ranks these seeds accordingly to the selectivity score that was used, and we see that most of the top seeds that were ranked do contribute significantly in uncovering the path. So looking at an example on the right, we see that FIXX discovers D paths for an application for all the applications that was used for the evaluation here, and it uses a similar modulo 2 with a seed value 3, and we see that the threshold optimal would be around 60%, where most of the paths are concentrated, because increasing the threshold beyond would aim to find paths that are exactly similar. And we try to not do that to reduce the number of false negative cases. So we see from the graph that as the similarity threshold increases, the number of paths uncovered decreases. Also, as the similarity modulo, which in this case is 2, if that would increase, the number of paths would increase as well, because we are, if we're trying to find exactly similar paths, increase in similarity would try to match the instruction node themselves for every node. That would increase the number of paths found. However, in our approach, we limit the similarity modulo to 2 and the threshold to around 50 to 70, so that we're able to obtain just paths that are exactly similar, but not leading into false negatives. So we conclude FIXX leads us to show that the number of similar paths uncovered is directly proportional to the modulo and inversely proportional to the threshold. Jumping into the results, we have FIXX discovering 1097 exploitable paths in 19 PHP applications, like I said, across 32 CV reports. And then out of all these results, we have submitted to Mitra, and we have received 10 new CVs that have been published. FIXX is robust in the sense that the original CV itself can also be rediscovered from the newly found CV, so it's a two-way approach. And the vulnerabilities that have been tested are both cross-site scripting and SQL injection, and FIXX has been successful in uncovering multiple similar exploitable paths for both the vulnerability instances here. Okay, so looking at its effectiveness, we also compare FIXX against 3 other approaches, NavX being a static and dynamic approach for detecting vulnerabilities, and RIPS being a static approach. and Clone Doctor being an AST-based tool for detecting clones of like code. So FIXX is able to detect multiple exploitable paths, as shown, a few of which are shown in the table here. And the approaches RIPS and NAVEX only detect a subset of these paths. And we do not present the results for Clone Doctor because Clone Doctor is not able to detect the similar blocks of code where the original exploitable path